Well, we just announced last year 2030 vision. Based upon that, we are making transition towards more electrification.
Right now are the biggest and most powerful vehicle that Mazda has ever built in the high-stakes world of auto innovation. One company dares to challenge the electric vehicle revolution, while giants rush to electrify. Mazda has been quietly plotting a course that could rewrite everything we know about automotive technology. Deep in their research labs, engineers have been developing something that whispers of transformation, a technological breakthrough that could turn the industry on its head. This isn't just another incremental improvement. This is a bold declaration of engineering prowess, a potential game share that promises to challenge our most fundamental assumptions about how vehicles should move, perform, and exist in our rapidly changing world. What is the new hybrid engine all about? Let's find out. The legacy of innovation. Mazda CEO recently made a bold declaration. The company's forthcoming engine is poised to disrupt the entire electric vehicle industry. This announcement has sent ripples through the automotive world, hinting at a groundbreaking development on the horizon. To appreciate the magnitude of this claim, it's essential to delve into Mazda's rich history and narrative marked by resilience, innovation, and a relentless pursuit of engineering excellence. In 1920, in the aftermath of World War I, Hiroshima's economy was in dire straits. Amidst this economic turmoil, a group of local businessmen founded Toyo Corkyo, aiming to revitalize the region by producing cork-based product. The company initially focused on manufacturing compressed corkboard, a venture that showed promise until a devastating fire in 1925 destroyed 70% of its equipment. This calamity could have spelled the end for the fledgling enterprise, but it instead set the stage for a remarkable transformation. In 1921, Jiro Matsuda assumed the presidency of Toyo Corkyo with a background in engineering and a visionary outlook. Jujiro steered the company toward diversification, recognizing the limitations of the cork industry. He initiated a shift toward manufacturing machine tools. This not only salvaged the company, but also laid the groundwork for its future endeavors in the automotive sector. By 1931, Toyo Kogyo, as it was then known, ventured into vehicle production with the introduction of the Mazda Go 3-wheeled open truck that bore more resemblance to a motorcycle with a cargo bed than to modern automobiles. This vehicle marked the company's inaugural step into the realm of transportation, embodying a spirit of innovation that would become synonymous with the Mazda name. The choice of the name Mazda for this vehicle was symbolic. It was derived from Ahura Mazda, the god of harmony, intelligence, and wisdom in Zoroastrianism, reflecting the company's aspiration to contribute positively to society through intelligent design and harmonious engineering. Additionally, the name resonated with the surname of the company's founder, Matsuda, creating a personal connection to the brand's identity. Then the outbreak of World War II saw Toyo Kogyo contributing to Japan's war efforts by producing weapons, most notably the Type 99 rifle series. The war left Hiroshima devastated, but the company's facilities remarkably survived the atomic bombing. In the post-war era, Toyo Kogyo faced the monumental task of rebuilding and redefining its role in a rapidly changing world. In 1960, the company made a significant leap by introducing its first passenger car, the Mazda R360. This compact coupe was a response to Japan's growing demand for affordable personal transportation. The R360 was well received, offering an economical and stylish option for the masses. Its success signaled Mazda's potential in the passenger car market and set the stage for future innovations. Their commitment to innovation became particularly evident in the 1960s when the company took a daring step by adopting the Wankel rotary engine. Developed by German engineer Felix W. Kell, this engine was compact and lightweight, offering a high-power tow-weight ratio. However, early prototypes were fraught with challenges, including durability issues that led to engine failures within hours of operation. Undeterred, Mazda's engineers embarked on an ambitious journey to refine and commercialize the rotary engine. Their perseverance culminated in the launch of the Mazda Cosmosport 110s in 1967, the world's first production car powered by twin-rotor rotary engine. This achievement not only showcased Mazda's engineering prowess, but also underscored the company's willingness to challenge conventional automotive norms. Still, Mazda's innovative spirit extended beyond engineering to encompass design philosophy. The company's commitment to creating vehicles that are both functional and aesthetically pleasing has been a consistent theme throughout its history. This dedication is particularly evident in the evolution of Mazda's design language, which has continually sought to capture the essence of motion and elegance in the Late 20th century, the company introduced designs that emphasized sleek lines and aerodynamic forms, reflecting a harmony between form and function. This approach not only enhanced the visual appeal of Mazda vehicles, but also contributed to improved performance and efficiency. The design philosophy has evolved over the years, culminating in the contemporary Kodo soul of motion design language, which embodies the dynamic beauty of life in motion. Mazda's journey has not been without financial challenges, however. In fact, in the late 20th century, the company faced economic hardships that threatened its independence. During this period, Mazda entered into a partnership with Ford Motor Company, which acquired a significant stake in the Japanese automaker. This alliance provided Mazda with much-needed financial stability and facilitated technology sharing between the two companies. Be it as it may, Mazda remained steadfast in preserving its unique identity and engineering philosophy. The company continued to develop its own technologies and maintain a distinct brand image. By the early 2000s, Ford reduced its stake in Mazda, allowing the Japanese company to regain greater autonomy and continue its pursuit of independent innovation. Although we are here to talk about the revolutionary engine and to understand why Mazda CEO is convinced it would take over EVs, we must first understand how we even got here. The evolution of engine technology. You see, the journey of engine technology is a testament to human ingenuity and the relentless pursuit of efficiency, performance, and environmental stewardship. From the rudimentary steam engines of the 18th century to the sophisticated internal combustion engines and the advent of electric vehicles, the evolution of propulsion systems has been a key component in shaping modern transportation. In the late 18th and early 19th century, steam engines emerged as a dominant force in powering machinery and locomotives. These engines operated by heating water to produce steam, which then drove pistons or turbines to generate motion, while revolutionary steam engines were bulky, inefficient, and required significant time to start, making them less suitable for personal transportation. The quest for a more compact and efficient power source led to the development of early gasoline engines. By the mid-98th century, inventors like Etienne Lenoir and Nicolas Otto had pioneered internal combustion engines that burned fuel within a confined space, producing immediate power. These engines were lighter, more efficient, and quicker to start than their steam counterparts. The practicality and adaptability of ICE technologies soon overshadowed steam, cementing its place as a preferred choice for automobiles as cars became ubiquitous in the 20th century. Concerns over fuel consumption, environmental impact, and performance led to a series of efficiency wars among manufacturers. The 1970s oil crisis spotlighted the need for fuel-efficient vehicles, prompting engineers to explore ways to extract more power from less fuel. At the same time, growing awareness of environmental issues led to stringent emissions regulations. Governments worldwide implemented standards to reduce pollutants like carbon monoxide, hydrocarbons, and nitrogen oxides. Manufacturers responded by developing technologies such as catalytic converters, electronic fuel injection, and variable valve timing to meet these regulations without compromising performance. As I have already mentioned, in the 1960s, Mazda introduced a rotary engine, a compact and lightweight alternative to traditional piston engines. Unlike conventional engines that use reciprocating pistons, a rotary engine employed a rotating triangular rotor within an epitrochoidal chamber to produce power. This design allowed for a higher power-to-weight ratio and smoother operation. However, the rotary engine faced significant challenges, particularly concerning fuel efficiency and reliability. Its design led to poor fuel economy and higher emissions, making it less environmentally friendly. Additionally, issues like apex seal were resulted in durability concerns. A rotary engine is an internal combustion engine using a different process. These drawbacks limited the widespread adoption of the rotary engine, leading Mazda to eventually phase it out in favor of more conventional technologies. In response to the dual demands of performance and fuel efficiency, the late 20th and early 21st centuries saw a trend toward engine downsizing. Manufacturers began replacing larger naturally aspirated engines with smaller turbocharged units. Turbocharging allowed these smaller engines to produce power comparable to their larger counterparts by forcing more air into the combustion chamber, thus enhancing combustion efficiency. This approach offered several advantages: improved fuel economy, reduced emissions, and lighter vehicle weight. However, it also introduced challenges such as turbo lag, increased complexity, and potential reliability concerns due to higher operating pressures and temperatures. Despite these issues, downsized turbocharged engines became prevalent, especially in markets with stringent fuel economy and emission standards. The late 1990s marked a significant shift with the introduction of hybrid vehicles. blending internal combustion engines with electric propulsion to enhance fuel efficiency and reduce emissions. The Toyota Prius, launched in 1997, became the first mainstream hybrid vehicle offering consumers an alternative that addressed growing environmental concerns without sacrificing practicality. Then the early 21st century witnessed the rise of electric vehicles spearheaded by companies like Tesla. Founded in 2003, Tesla aimed to accelerate the world's transition to sustainable energy. The launch of the Tesla Roadster in 2008, followed by models like the Model S, demonstrated that EVs could offer impressive performance, range, and desirability. Tesla's success prompted traditional automakers to invest heavily in EV technology, signaling a potential paradigm shift in the auto industry. But while many manufacturers pivoted towards hybrid and electric technologies, Mazda embarked on a mission to refine and perfect internal combustion engines. This commitment culminated in the development of the Skyactiv technology suite, aimed at improving the efficiency and performance of vehicles. A standout achievement of this initiative was the introduction of the Skyactiv X engine. This groundbreaking engine combined the benefits of gasoline and diesel technologies by employing the spark control compression ignition. In essence, it allowed the engine to ignite a lean fuel mixture through compression akin to a diesel engine, but with the responsiveness and higher RPM capability of a gasoline engine. The result was an engine that offered improved fuel efficiency, reduced emissions, and engaging performance. However, as we'll explore, even this innovative approach faced limitations that stressed the complexities of modern automotive engineering and showed all the downsides of the modern approach to industry. What am I talking about? The harsh reality of modern cars. Well, as you know, electric vehicles have been lauded for their zero tailpipe emissions and potential to reduce our carbon footprint, yet the production of EV batteries raises significant ethical and environmental concerns. The extraction of lithium, cobalt, and nickel, key components in battery manufacturing, often involves environmentally destructive mining practices and has been linked to human rights abuses in certain regions. Moreover, the energy-intensive processes required to produce these batteries can offset some of the environmental benefits gained during the vehicle's operational life. The widespread adoption of EVs is also hindered by infrastructure limitations. Charging station shortages remain a significant barrier, especially in rural and underserved areas. On top of all, concerns about the power grid capacity to handle the surge in electricity demand pose questions about the scalability of EV technology. Upgrading the grid and expanding charging networks require substantial investment and time, factors that can slow the transition to an all-electric future. While EVs are often marketed as low-maintenance alternatives to ICE vehicles, they are not entirely free from upkeep challenges. Battery degradation over time can lead to expensive replacements, and specialized components may require service from technicians with specific training, potentially increasing maintenance costs, while the initial purchase price of EVs remains higher than many comparable vehicles. Hybrid vehicles, which combine with electric propulsion, offer a compromise between traditional and electric driving. However, this dual-system approach introduces a whole new set of challenges. The integration of both an engine and an electric motor, along with their respective control systems, can lead to higher production costs and potential maintenance challenges. Battery replacements in hybrids, though less frequent than in full EVs, can still be costly and may deter potential buyers concerned about long-term ownership expenses. In an effort to meet stringent fuel economy and emission standards, many manufacturers have turned to downsized turbocharged engines. While these engines can deliver impressive power relative to their size, they often operate under higher pressures and temperatures, which can affect durability. Owners have reported issues such as increased wear and tear, leading to higher repair costs over time. This trade-off between performance and longevity raises questions about the long-term viability of such engine designs. This is why Mazda chose a path less traveled. The company resisted the trend of adopting hybrid technology wholesale, operating on the belief that the internal combustion engine still held untapped potential. This conviction led to the development of the Skyactiv X engine, an ambitious attempt to redefine what ICC could achieve in terms of efficiency and performance. It was heralded as a groundbreaking development, utilizing spark control compression ignition to combine the benefits of gasoline and diesel engines. This technology aimed to deliver improved fuel efficiency and reduce emissions without sacrificing performance. However, real-world applications revealed a more nuanced picture. While the engine did offer better fuel economy compared to its predecessors, the gains were not as substantial as some had hoped. Additionally, the complexity of the system was challenging to manufacture and maintain. Oh yeah, The Skyactiv X engine also faced criticism regarding its performance characteristics. Some drivers noted that the engine required higher RPMs to deliver power, which could affect driving dynamics and overall satisfaction. As if all this wasn't enough already, the scalability of the technology was also questioned. Implementing this system across different vehicle models and meeting varying performance expectations proved to be a daunting task. Mazda's engineers were acutely aware that despite the strides made with Skyactiv X, the engine was not the definitive answer to the industry's evolving demands. The rapid pace of technological advancement and shifting consumer preferences signaled that further innovation was necessary. This realization set the stage for Mazda to explore even more radical solutions in their pursuit of automotive excellence, ultimately leading to the new engine their CEO promises will destroy the entire EV industry. But hold your horses, we are getting to that really soon. The search for the ultimate solution. The thing is that in the search for the ultimate engine, many automakers have tried to rewrite the rules of internal combustion. Over the years, some truly revolutionary ideas have emerged, each promising to change the future of cars. But as promising as these technologies seemed, none of them managed to become the definitive answer. They all had flaws, some practical, some mechanical, and others simply a matter of cost. Yet, each of them played a role in shaping what's coming next. Take hydrogen combustion engines. For example, companies like Toyota and BMW have been investing in this technology, hoping to create an internal combustion engine that burns hydrogen instead of gasoline. On paper, the idea is perfect: a familiar engine layout, an existing manufacturing process, and an exhaust that emits only water vapor. Hydrogen-powered combustion engines could, in theory, offer the best of both worlds, the efficiency of hydrogen fuel without the need for massive battery packs. But in reality, it's not that simple. Hydrogen storage is one of the biggest challenges. To keep hydrogen in a usable state, it needs to be compressed at extremely high pressures, up to 700 bar, which means manufacturers have to install reinforced tanks that add cost and weight to the vehicle. On top of that, hydrogen refueling infrastructure is severely lacking. Unlike gasoline stations, which are everywhere, hydrogen stations are rare, and building them is expensive. And then there's the efficiency problem. Even though hydrogen combustion engines don't produce CO2, they still create nitrogen oxides, pollutants that contribute to smog and air quality issues. These factors have kept hydrogen combustion engines from becoming the industry standard, despite decades of development. Another radical innovation came from Koenigsegg, a company known for pushing the limits of engineering. Their free valve technology was supposed to revolutionize internal combustion by removing one of the engine's most fundamental components, the camshaft. Traditional engines rely on camshaft to open and close the intake and exhaust valves at fixed intervals. Free valve technology, on the other hand, replaces this with an electro-hydraulic system that allows for completely independent control of each valve. In theory, this allows an engine to adjust its operation in real time, optimizing fuel economy, power, and emissions far better than any conventional setup. It could even switch between different fuel types with minimal modifications. But the problem? Complexity. Free valve technology is expensive to develop and manufacture. And while it's been tested in high-performance supercars, it hasn't been widely adopted in mainstream vehicles. The system requires intricate sensors, actuators, and hydraulic components, all of which add to the cost and potential maintenance issues. For an industry that prioritizes reliability and cost-effectiveness, free valve hasn't been the breakthrough some had hoped for, at least not yet. Then there's Nissan's attempt to reinvent the combustion engine with their variable compression turbo, or VC turbo for short. Unlike traditional engines, which have a fixed compression ratio, the VC turbo can adjust its compression on the fly. This means it can switch between high compression mode for better fuel efficiency and low compression mode for maximum power. The idea was to create an engine that offers both performance and fuel economy without the drawbacks of conventional turbocharging. The execution, however, hasn't been perfect. The VC turbo's mechanism, which physically adjusts the length of the piston stroke, add complexity and moving parts to an already intricate system. More parts mean more potential points of failure. Some reports have suggested durability concerns, particularly with long-term reliability. While Nissan has made progress in refining the technology, the added complexity has made it difficult to scale beyond a niche market. The engine works, but it hasn't changed the industry the way Nissan had hoped. Meanwhile, Porsche has been pursuing a different route, one that doesn't require rethinking engine mechanics but rather the fuel itself. Their answer: synthetic fuels, or e-fuels. Unlike traditional gasoline, which comes from crude oil, e-fuels are made by capturing CO2 from the atmosphere and combining it with hydrogen to create a fuel that burns just like gasoline, but is theoretically carbon neutral. The advantage is obvious. Existing gasoline engines can use this fuel without any modifications. No need for new engines and no need for new infrastructure, just cleaner fuel. But once again, reality has a way of complicating things. Right now, e-fuels are prohibitively expensive to produce. The energy required to synthesize them is immense, and without a massive investment in renewable energy, scaling production remains a challenge. Current estimates suggest that e-fuels cost about 10 times more than regular gasoline, making them impractical for everyday use. The technology is promising, but unless production costs drop significantly, e-fuels won't be replacing gasoline anytime soon. And that brings us back to the central problem. Despite all these attempts, no one has truly cracked the code. Hydrogen combustion engines, free valve, VC turbo, and e-fuels have all pushed the boundaries of what's possible, but none of them have been the ultimate solution. Each one has had its share of compromises, be it cost, complexity, or infrastructure limitations. And that's why Mazda wasn't convinced that any of these were the future. For years, Mazda engineers have been quietly working on something that could be different, something that doesn't just tweak existing designs but redefines what an internal combustion engine can be. What if they had found a way to combine the efficiency of diesel, the responsiveness of gasoline, and the environmental benefits of hybrid technology? What if they had created something that could challenge the dominance of electric vehicles, not by resisting change, but by leading it? That's exactly what they claim to have done. And now it's time to find out how Gen Z Mazda is poised to revolutionize the automotive industry with its forthcoming Skyactiv Z engine, a next-generation four-cylinder powertrain set to debut in 2027. Designed to replace the existing Skyactiv G and Skyactiv X engines, the Skyactiv Z aims to deliver exceptional fuel efficiency and performance while complying with stringent emission standards such as Euro 7 in Europe, as well as the LEV4 and Tier 4 in the United States. According to the company, the Skyactiv Z engine is very close to the ultimate combustion, suggesting a significant leap forward in IC technology. Will provide mild hybrid, plug-in hybrid, and BEV. This development reflects Mazda's commitment to enhancing traditional engine designs, even as the industry increasingly shifts towards electrification. Insiders from the company suggest that whenever he is asked about this engine, Mazda CEO simply says, "Our new hybrid engine will destroy the entire EV industry." Mark my words. As I've made my decision, I will not hold back until Mazda is on the very top of the modern car industry. And if that means we have to make hybrid engines, we will make the best of the best. But is this really possible? Well, yes. You see, by focusing on hybrid technology, Mazda aims to address consumer concerns about EVs, such as limited range and charging infrastructure, while providing a familiar driving experience with improved efficiency. The Skyactiv Z engine is expected to debut in the next-generation CX-5, integrating a hybrid setup developed in-house, which aligns with Mazda's vision of delivering vehicles that meet evolving environmental regulations without compromising performance. And they even say the new set of cars would come at an affordable price. While many competitors invest heavily in battery electric vehicles, Mazda's development of the Skyactiv Z engine demonstrates a belief that advanced internal combustion technologies can coexist with electrification to offer consumers a range of options, without having to spend hundreds of thousands of dollars for the car or even spare parts. Now be honest, would you consider buying this new Mazda?